I'd like to talk about dynamos at the galactic scale. And this is work done with Fred Gant and Marc-Antoine at Alto. And at the end, I'll bring in some results from David Whitworth at Lyon, who will then amplify on those results during the next talk, because I just want to make a short point about them. Okay, so there are two types of dynamos that are relevant for producing. Actually, you know what? I'm going to start with. No, I think I'll start with this. Actually, no, I'll start with this. Okay. When we observe galaxies, we can see polarized emission, indicating that they have large-scale and relatively strong magnetic fields. How did those fields come from an early universe that was surely almost free of magnetic fields? There are two types of dynamos that are probably relevant to growing magnetic fields at the galactic scale. First, there's the small-scale fluctuation Kazantsev dynamo, which predicts that if you have a wide variety of turbulent velocity fluctuations with some spectrum, perhaps Kolmogorov-like, that it will predict exponential growth in the magnetic field at the dissipation scale. So the smallest scale velocity fluctuations are the ones that are driving magnetic field growth. And this has a consequence that as the magnetic energy exceeds the viscous scale kinetic energy, that this will tend to saturation. And indeed, we see from numerical models saturation at about 1% of equipartition with the kinetic energy of the flow. However, it's exponentially growing, so it's very fast, and it grows on the eddy turnover timescale, which is short in a galaxy. The other sort of dynamo is the large scale or alpha or omega or mean field dynamo. And that relies on living in a shearing flow that can take loops of field, stretch them, twist them, and reconnect them to make more flux. And so you get these stretch, twist, fold. That grows large-scale ordered mean field, but it grows on the orbital time scale of the system, which for a galaxy is long. Quarter of a gig-year for the Milky Way, of course. Shorter for smaller galaxies, but still very long. Now, because the classical alpha-omega dynamo requires many orbital timescales to grow a field, and if you're starting from very small values, that's not going to work very well, particularly since there are already strong fields being observed at redshift 2.5, so 2.5 gig-years after the, coincidentally, after the Big Bang. And given that galaxies don't start forming until 0.5 gig-years or so, this is, of any sort, even little tiny things, this is a very long period. Therefore, the small-scale dynamo is probably the dominant initial source of magnetic field, but then it has to be ordered to match the observations with a subsequent large-scale dynamo. So then we address the question here, how do you transition from a fast turbulent dynamo, which produces one set of field structures, to an ordered dynamo, large-scale dynamo, that produces a completely different sort of field structures? Quickly.
Sorry, at small scales, who gives you this seed of magnetic field? I mean, some time ago we did some...
Ask me that, that's a long discussion. Ask me that during the questions, and I will give you an answer. Sure. Okay. Two answers, at least. Okay, so looking at how do we drive a small-scale fluctuation dynamo, back now 20 years ago, Dinshaw Balsara and I and others showed that supernova-driven turbulence would drive a fluctuation dynamo. Here's our exponential growth of the magnetic field, and this is what the magnetic pressure and the gas pressure looked like. Now, this was done with a second order numerical code, and in the last 5 years or so, questions were raised, could this be tangling rather than an actual dynamo? And so we wanted to address that. And so we came back with a modern code, pencil code, sixth order instead of second order, and with explicit Laplacian resistivity and viscosity. We did not rely on grid viscosity as we did back in the day. But again, using supernova shearing, supernova driving for the turbulence. So here's an example of the magnetic pressure and density for one of our models. This is, I think, 256 parsecs across. And you can see that we're, again, driving turbulence. And in the regions outside of the superbubbles, we're getting field growth. And if we and then we checked to see, are we in fact resolving this flow sufficiently well that the explicit resistivity is stronger than the numerical resistivity? And the answer is that when we change the explicit resistivity, we indeed see the expected extension of the power spectrum. So yes, we really are truly doing physics here and not just numerics. And this is the kinetic energy, which shouldn't feel any change when we change the resistivity, and indeed it doesn't. But we can do the same thing for the viscosity. Okay, now, if we do a resolution study, that was at high resolution, but at low resolution, the numerical resistivity dominates. And the answer is that at 4 parsec resolution, it took us hundreds of megayears to grow the same field that grew, this is a log scale, that grew in under 10 megayears at 0.5 parsec resolution. So again, this is a log scale, so it matters dramatically whether you have enough numerical resolution in order to get down to some sort of physical resistivity scale. It gets worse. If you go out to 10 parsecs, it takes 2 gigayears. And indeed, Reeder and Tessier quantified this. So from 36 to 9 parsecs, they went from a growth time of 500 megayears to 75 megayears. Again, bearing in mind that at half parsec resolution, the growth time is well under 10 megayears. Okay.
Excuse me, Mordecai, can you quantify the variation in resolution here in terms of multiples of resolution of the Kolmogorov dissipation scale rather than the physical units?
Not in the middle of the talk. Ask me again and I'll try and come up with some numbers. But think about it. It's several zones per at the inner scale. And these are like 256, 512 zone sort of models. Okay, so let's look at just how much advantage did we get from using sixth order. So this model with resolution 0.78 parsec can be compared for the second order code, can be compared to the same parameters with the sixth order code. And you can see the sixth order code grows dramatically faster. That is, we have much less numerical resolution. We're getting much closer to the physical diffusivity there. Okay, I posed an intermediate question. Is this field tangling or dynamo? So we started with some toy models of uniformly forced boxes. And here is one where we suppressed, here's one where we suppressed the dynamo by increasing the resistivity so that we only had field tangling. And what we see is we get large scale field, but it drops off dramatically below the forcing scale. On the other hand, when we had a lowered resistivity so that we could drive a dynamo, then we get a large range of of power, down to very small scales, which is expected for the dynamo that drives primarily near the dissipation scale. When we then went and looked at our supernova-driven models, the forcing scale for supernovae is around 100 parsecs. And so if you look at this, we're not getting a dramatic drop-off right below 100 parsecs. It's extending over more than an order of magnitude beyond that. So we argue that that's a dynamo. The chair, should I accept questions and you'll give me something in the discussion? Okay, quickly.
What do you mean by tangling here? Do you mean just a linear shear acting on the magnetic field, or what's the tangling?
Just taking field lines and moving them around, not just a linear shear.
You need to stretch.
Yeah, stretching. Any sort of stretching.
Isn't that defined?
Okay, so like I said, come back at the questions for that level of detail. Okay, so isothermal models were argued to show a dependence of growth rate on Mach number, and here's Fedoroth et al. Showing that. These are the highest Mach number models, and whoosh, they go up real fast. However, in our compressible multi-phase medium, the same behavior is not seen. So this is Mach number this way, and this is growth rate. And there's no particular correlation. On the other hand, what we do see is that the hot medium, okay, so the diamonds are the highest resolution models here, so you probably want to follow them. And I'm showing cold, warm, and hot being 1,000,000 Kelvin, warm being 10 to the 4, cold being a few hundred, showing their field growth rate. And the answer is that, first of all, the field grows much faster in the hot medium, as expected, because the eddy turnover time in high sound speed gas is much faster than in the cold medium. And it correlates extremely well with the local vorticity. So the turbulence is driving the dynamo growth rate. The magnetic Reynolds number, local magnetic Reynolds number, the local Mach number are not well correlated. Okay, the magnetic Prandtl number has been hypothesized to control the dynamo. We did not find that. What we found is that it's the actual magnetic Reynolds number that's important. So if we vary the magnetic Reynolds number to change the Prandtl number, holding the viscosity constant, we get dramatic changes. If we hold the resistivity constant and vary the viscosity, we get very little change. So it's not the Prandtl number is not the invariant. It's the magnetic Reynolds number. This is just to show you what. Okay, then we did a stratified models so that we can start thinking about the shearing flow. Those were all periodic boxes, but now we've got stratification and ultimately shear. And just to show you what we're up to here. And okay, not too bad. So now we have stratified shearing supernova-driven compressible turbulence. This all has cooling so that we maintain a three-phase medium. And what we found is if we remove the large-scale field, okay, we still get the small-scale dynamo. Note that we just started at lower initial field, but otherwise it matches this slope. And if you look carefully, what you'll find is that when we add the large-scale dynamo, that is, allow it to grow by not removing the large-scale field, we actually depress the small-scale dynamo somewhat. So what happens is, I got that backwards, didn't I? No. When we allow the small-scale dynamo, the large-scale dynamo actually is depressed a little. So the small-scale dynamo is actually robbing energy from the large-scale dynamo during the transition phase. It's not a huge effect, but it does show that they are interacting and indeed mildly destructively. But in the long term, the large-scale dynamo heads off, merrily heading towards equipartition. Now this is only 1.75 gigayears, We're still running these models actually, but here's a high resolution model. You can see that we, as expected, pop up and then 5, perfect, and then start moving towards equipartition. Okay. And indeed, we can see the growth of the large-scale field. This is a time history. At first, the small-scale dynamo grows, but then you can see the large scales, low wave numbers coming up. Or another way of looking at it is if you look at the different components. So this is the lowest K mode, and this is the highest K mode. The highest K mode starts out dominant, but then as the large-scale dynamo picks up the mean field, the lowest K mode becomes dominant. And we find that as the dynamo grows, particularly the large-scale dynamo grows, we also get organization. And so the toroidal field actually undergoes field reversals while it's growing and then becomes dominant in a single direction. This is the normalized field. This is the actual field. So you can see the geometry changing. And again, we made the point that changing the resistivity, not the Prandtl number, determines the structure and the parity. Okay, now, one effect of this appears to be to determine the magnetic field density relation in low-density gas. So this is work that David Whitworth led, in which we went back and re-examined the question of if we take observations, either Zeeman measurements or Davis-Chandrasekhar Fermi measurements as compiled by Patel et al., what is the behavior of the low density and high density relationship? And so we got what we fit a slope and a breakpoint. So a breakpoint at B naught, N naught, and slopes below and above. And what we found was there was always a moderate slope in the low density medium, the alpha 1. There's also something between 1/2 and 2/3 for an alpha 2 slope. It's somewhat indeterminate given the available data. And a N naught at moderate density and a B naught that can get quite high. So recently, like this year, Amit Seda and Naomi McClure-Griffiths took the pulsar measurements and put them on the same plot, and we were gratified to see that our fit using DCF and Zeeman actually also runs through the pulsars, and certainly they agree with the idea that there is a relationship in the low density gas. And finally, we compared the values for alpha 1, alpha 2, B naught, and N naught observed, which is these 2 points, to a wide variety of models. And the models that mildly got favored were the ones that had a full dynamo, that is a full rotating disk, or shear in a well-resolved zoom-in region in a disk, and that, that those were what were required to reproduce the observations. So, conclusions? I think I actually have time for conclusions because I spoke really fast. Is that we had a supernova-driven ISM can drive the small-scale dynamo, that you need to resolve the supernovae, including the cooling. So that requires resolutions under a parsec. You need to resolve some sort of resistive scale. Now, we're not claiming that we're using a realistic resistivity. So the values that we saw of like 10 megayear growth times may still be overstated. The turbulent dynamo may actually grow even faster. And indeed, models of magnetic field growth during first star formation already suggest reaching equipartition during the initial collapse, like Muhammad Ishtar's work. Much less in the disk, something that Ralf Klessen and his group have found. So you get magnetic fields very quickly. As soon as you have stars, you already have fields. The turbulent dynamo, the SSD, doesn't reach equipartition, and so you need to use a large-scale dynamo, and the magnetic field density relationship also appears to be set by this behavior. Now I'll take all your questions. Thank you.